I'd like to I just want to quickly review what we talked about last week, and that is the idea of distribution of a normal population. And I'm just going to go over this real quick. And we were talking about how in a normal distribution, we find that most of the values are somewhere in the middle. For instance, if we're looking at height, we people, let's say the average height is 68 inches in a population. It happens to be a particularly tall population, I guess. 5'8" average is, I guess, a little bit tall for an average. Um, um, and then as you get to, like the shorter heights, 66 inches, 65, 64, well, those are going to come up less frequently. And as you get further away from the average height, you get fewer and fewer people that are that height. Same thing going the other direction. And a normal distribution like this, where a particular individual lies within this group, if we sample one person in that population at random, where that person lies in this distribution is random. In other words, I might pick a person that's taller than average, might pick a person that's shorter than average, but I'm more likely to pick somebody that's in the middle than somebody that's either of the extremes. And we know that this distribution, if we take a big enough sample, begins to look like a bell-shaped curve like that. And we know that if the mean, I'm going to make a mean of 100 and a standard deviation of 5, the mean is 100. We know from the empirical rule that 95% of the values, 95% of the people in this population lie between two standard deviations below the mean, 90, to two standard deviations above the mean, 110. We also sometimes call that a z-score, -2, and a z-score of +2. That's a rough estimate. Okay, one way to look at it is that that's the percentage of the population that's within that bound, and for -1 and +1 standard deviations, it was about 68%, and so on and so forth. Okay, we can look at it in terms of like the way the population is distributed. We can also look at it in terms of probability. What's the probability that I would choose someone with a height that's greater than 110? Well, the probability I would choose someone that has a height greater than 110. Well, this is the percentage of people in the population that have a height greater than 110. So that's the probability that I would choose someone at random has a height greater than 110. And we know because we did a little deduction based on what we knew from the empirical formula that this is 95%, and this part of the curve is going to be symmetrical to this part of the curve, percentage of people less than 90, and that's going to add up to 5%, what's left from 95%. So that percentage is going to be 2.5%. Good. Thank you very much, guys. Okay. So we can use the empirical formula or empirical rule to make these rough estimates. We took that a bit further. We said to ourselves, well, what if we're looking for the percentage of people in this population that are above 103? Well, 103 represents everybody, above 103 represents everybody from this point up. Okay, so everybody from that point up is, let's see, what is the z-score that represents 103? Well, 103 is 3/5 standard deviations above the mean. Okay, well, that's, in other words, that's 0.6 above the mean. Okay, one way to do it is just just by interpretation. 103, 3 above the mean. Standard deviation is 5, so it's 3/5 of a standard deviation above the mean, or 0.6. The other way I could do it is just a simple formula: the value we're interested in minus the mean over the standard deviation. Okay, and that was 103 minus 100 over 5, and that of course comes out to the same thing. 3/5 or 0.6. Problem here now is that how do I know what that value is? Okay, what is that area of this distribution? And we know that we have a table that we can go to called the ZTable. Okay, I'm going to pull up the one that's in the Agresti because it's a little bit easier to work with, and we know that we can find the z-score from the column and the row at the top here. So z-score of z-score of 3.35 would be negative 3.3 and then 5 over here, a very small area because it's way down. And that represents this number represents the area or the percentage of the distribution that's below that z-score. Well, this is all negative z-scores on this particular page because it represents everything from the mean to the left. The mean has a z-score of 0, right? In other words, 0 minus 0 over sigma is going to be 0. So the z-score of the mean itself is 0. Okay, so if I want to know if I have a value above the mean, well, on some tables they force me to use that table and use my knowledge of how the normal distribution is symmetrical to make a deduction as to what area I'm working with. But in the Z-table and Agressity, they're a little bit more gentle, and they actually give you positive z-scores as well. So a z-score of 0.60 would be, the third digit being a 0, would be 72.6%. Okay, I rounded that off a little bit, 0.7257 or 72.6%. So in other words, that tells us, because that's the way the table is set to work, that everything from this area down is 72.6%. Okay, that out of 100%, that leaves 27.4%. So the probability of a randomly selected person being above 103 in this particular population is 27.4%. Okay, we use a z-table to figure that out. We also know that we can use the formula, we can use norm, the function equals norm dist in Excel to give us this value as well, or norm s, I think norm s dist. Okay, but there's functions in Excel that'll give us this value as well. I think you can see that on the previous. Well, let me just do it, just so that we remember. I just want to go over this to make sure that we're all at the same starting point here. Okay, I'm going to go in here, and I'm going to start here. Let me blow this up. See, view. Okay, and I'm going to say equals norm, whoops, norm s dist, parentheses. Okay, and well, I don't want to use that, but it asks me, norm s dist asks me to provide the z-score for the value, the area that I'm looking for. So I'm going to write in 0.6 and close parentheses. And it comes up with the area to the left of that point, 72.57, the same number that we got before. There's other functions and other ways of doing this. Norm dist, parentheses, asks me for the value I'm interested in, 103, comma, the mean, 100, comma, the standard deviation, 5, comma, and cumulative, which means that you want the area just of that for that one value, which we almost never want. We usually want to get the whole cumulative area to the left of this, just like the table works. I'm going to say true. We want cumulative value, and it comes up the same way. So there's a lot of ways to skin a cat in Excel. So at any rate, so that's what we did. We played with the Z-table. When we couldn't use the empirical rule, we used the Z-table instead. So we're going to pick up from that point. Now, I want you to notice one thing here. Whenever I dealt with this distribution, I always used mu for the mean and sigma for the standard deviation. Can anybody tell me why I used mu and sigma? Why did I use Greek letters? Okay, I know somebody knows. Okay, that's right. We're dealing with the population. Anytime when we actually deal with the population mean, population standard deviation, we use Greek letters. Anybody know what we call those kind of that information when we're dealing with the population? This might be a little bit too vague, right? That's called a parameter. Okay, when we're dealing with the population, we're dealing with parameters. Mu is 100. Sigma, standard deviation, is 5. Okay, when we're dealing with a sample from the population, we're dealing with a statistic. And since we're taking statistics, that's pretty much a dead giveaway that, like almost everything we're ever going to do in this math or science is going to be involved with statistics, samples from a population, not the population itself, right? We're not census takers. We're epidemiologists and biostatisticians. So we're going to be working with statistics for the most part, or samples for the most part. So that's an important distinction because samples, when we take a sample, what we're trying to do is we're trying to take a small group randomly selected from this population, and we're trying to understand how this population is distributed based on that small sample. In other words, if we hadn't known anything about this population, we might have taken a sample of 100 people and averaged that sample of 100 people and said, well, we took 100 people out of, like, say this population has 100,000 people in it. We took 100 people at random, so we're going to take their heights, and as it turns out, their average height is 68, and average height of the sample is 67.6 inches. Well, maybe the population was 68 inches, but because we took a relatively large sample, like 100 people, well, we have a bit of confidence that we're going to be pretty close to the sample. If I were only going to take a single person, right, then I could grossly underestimate the average height of the population, or overestimate it if I only relied on a single person, a sample of one person, or a sample of even 2 or 3 people, or 5 people. The larger the sample is, the greater level of confidence I have that I'm estimating the real mean for this entire population. Same goes for the standard deviation. I have more confidence than I have a better estimate of the spread or the distribution of the population if I take a larger sample as well. So we're really interested in samples, and samples behave in a very interesting way. Okay, and we're gonna give that a try right now. What I'd like you to do is go to this table that we produced, and I also want you to open up something that's called a random number table. Okay, chances are you guys haven't worked with one of these before, and the deal here is that you and I, we want to take a sample of a population, and in order to evaluate that population and not get a biased view of it, we want to sample that population randomly. We want to pick out people from that population completely, totally without bias. Okay, so we need to find a way to select those people in a truly random manner. Well, where do you get a random? How do you get random? In other words, if this represents my population, this 100 numbers, okay, and I've identified these all represent people, for instance, and I've identified each one of these people by a row and column. So, for instance, this person over here, 00, is 61 inches tall, and 23 is 45 inches tall, and 68 is 49 inches tall. These really are just numbers. I'm just assigning heights to it right now, but they could be anything. Doesn't really matter as long as it's something that's normally distributed. Okay, so I could take a look at all of these things, and I could say to myself, okay, I'm gonna see if I can't. Okay, let me see if I can't find my Excel version of this file. Here we go. I got an Excel version of this same file. I'm gonna click in here. And I'm gonna say equals average. I'm gonna call this 100 people my population, and I'm just gonna select all of them and find the average for this population of 100 people. The average happens to be 50. Now, I'm also going to calculate standard deviation. Okay, and I'm going to highlight all 100 of these numbers. Notice I'm not going all the way out to the edge to the red numbers, which are just there to identify position. Okay, this population has a mean of 50 and a standard deviation of 9. I probably have these cells rounded off, so it may not actually be exactly 50 or exactly 9, but close enough for what we're going to be doing. Okay, so now let's say that This could have been a population of 1,000 people or 10,000 or 100,000. Let's say that we do not have the resources. We don't know what these numbers actually are. We don't have the resources to go out. We want to find out what the average and standard deviation for this population is. We don't have the resources to go out and sample all of the people in the population. We can only sample a sample size. We can only afford to sample a sample of size 9, okay, n equals 9. Okay, so we want to go in here and we just want to sample from this population randomly. Well, how am I going to sample randomly? If I'm right-handed, for all I know, I might pick more numbers on the right-hand side. If I'm left-handed, I might pick more on the left-hand side. If I'm ambidextrous, I might pick them on both extremes. If you're playing the lottery, you don't want to ever go, don't ever want to play 1, 2, 3, 4, 5, 6, because there are thousands of people that play 1, 2, 3, 4, 5, 6. And if it wins, you're going to have to split the money with a ton of people. You don't ever want to go straight across the top line. You don't want to go diagonally. You don't want to go, in a fixed pattern, because many people are going to be doing the same thing. That's not a random selection. So how do you get a random selection? Well, you can get it from them automatically. I got a suggestion of every X person, like every fifth person. That's not really random either, because maybe there's some sort of bias in the collection of this data that, in the order in which these people might be available, that might bias that. So we need really something that's completely random. In the lottery, they will actually have the machine calculate random numbers for you, right? You can do a quick pick and it'll calculate random numbers. In Excel, for instance, years ago, they used to create random number tables using a computer or a calculating device. Sometimes even using some natural phenomenon that has a certain random quality, like the production of like a radioisotope decaying and the production of particles coming from it. Okay, and they would actually track that and use that to build a table like this table. Okay, I just want to show you in Excel that is possible to do it, to do this in Excel. There's a function in Excel called rand. Let me go down here, equals RAND, parentheses. You don't have to give it a value. See, notice in the prompt, there's no value in the middle. This produce, I'm going to have to actually go up here, format, and give you some decimal places in this case. Okay, let's do 2 decimal places. Rand gives you a random value. If I click in there again and if I do it down here, equals rand, parentheses, it actually gives me a new random value. I'm gonna do a few numbers here. Cells. Let me give it a couple of decimal places, right? And so on. Notice every time I recalculate, it recalculates the other random numbers as well. So in one case it was 1, one case it was 98, equals rand, parentheses. Let's see what I come up with this time. 93, 47, 65, 93. So these are random, a series of random numbers generated by Excel. You can get them in other places too. There are tables of random numbers that have been generated for you. Okay, and the way you would use a table like this is you would pick out a random location to start from. For instance, let's say I start from here, 25. Well, remember, each one of these people, my subject number for each one of these people is defined by a column and a line. So 25 would be, the person 25 would have a value of 46. Row 2, column 5. Who should I pick after 25? Well, next person I'm going to pick, well, 25 comes up again. I'm not going to use that. So I'm going to use 54. 54 are the next 2 numbers. 54 would be the 5th row, 4th person would be 67, and so on and so forth. So you could either use these straight across, you could use these in a column, and so on and so forth, but just keep going the same direction. Yeah, the file should be available on Blackboard for you as an Excel file. Yeah, it's pasted into Excel as a picture, so you can't actually copy it into Excel, but you should have an Excel file on Blackboard. Okay, so now Let me know if you can't get to it. I can quickly upload it if we need it. But you should see an Excel file on Blackboard. Okay, so now you may not need it right now anyway, because what I'm going to ask you to do, and I'll leave this picture up here so you can do it. What I'm going to ask each of you to do, or as many of you as I convince to do this, I want you to take a random sample from this population of 100 of a sample size 9. So start somewhere in this table. Don't start with 25. That's like picking the lottery tickets like everybody else. I don't want you guys all starting from the same point I did. Pick your own point to start. There's a few pages of this stuff. Pick your own. I'll leave this open as well, so you can kind of, if you want to get down to it as well. I'll pull this back up again, so you can see a lot of it if you're stuck and you have no other access to it. I would like each one of you to I'm chuckling because I'm getting comments every once in a while. I'd like each one of you to take a random, start with one point and take a random sample as I just did. For instance, if I started from there, it'd be number 34. 3, 4 would be 63. So I'd write 63 down. Next one might be 76, would be 28. And write that number down. I want you to get 9 numbers. When you get those 9 numbers, I want you to find the average of those 9 numbers and the standard. Just give me the average of those 9 numbers. That'd be fine. Okay, so each one of you is going to give me one number, which is going to be the average of a sample of size 9 from this population. So I'm going to give you guys a few minutes to give that a try. Just go ahead and type in the number that you get into the chat box. Okay. Again, what you're going to do is you're going to go to the random number table, this table over here. You're going to pick out a spot at random to start. So I'm starting at 67. So I'm going to take that 67 and I'm going to use that to represent the row and column number 6 and 7. So the number that's in the row 6 and the column 7 is 50. I'm going to write that number down or put it into Excel, 50. Then I'm going to go back to where I was and say the next number is going to be in the 9th row and the first column. 9th row and the first column happens to be column 1. Then notice you can also have 0. 9-1 happens to be 46. So I would add 46 to that first number. And so on and so on and so on until I have 9 numbers randomly selected from this population. Once you've done that, add the 9 numbers together, divide by 9, and just type in the average into a chat window. I'm going to wait until I get a bunch of you guys doing that. I'm probably going to need some, at least 10 or 12, 10 or 20 results. Okay, we're getting there. Do your best on it. I don't need everybody doing it, but I do need a decent a decent number of you. So you can see that we're getting some different numbers. Getting some higher than 50, some lower than 50. We know that the actual average is 50. Okay, I'm gonna round these off. You can round these off to whole numbers if you want. I see a couple of you have taken me up on the offer to let you post anonymously. Okay, I'm gonna pull up Excel now because I'm gonna start to collect some of your answers. And if you don't see, you may notice me actually round a bit, so don't get mad at me if I round. Hopefully I'm not cutting you off there, but okay, let me back up here and write a few numbers down. Oh, I got a bunch. Wow. Okay, pretty good response this time around. Okay, you guys can stop. 54, 50, 50, 54, 50, 47. 52, 42, 51. Okay. I got that 42 already. 53, 51. 53, 51. Got to go back up there. 51, 48. 51, 48. Every time you guys do this, it jumps down to the bottom. I have to scroll back up. 48, 49, 49, 43, 58. 49, 43, 58. Okay, I'm going to take a few more. 50, 49, 51, 52, 59, 55, and 46, 45. I think I got about enough here. 49. Okay, I'm going to stop there. And if, okay, hang on a second. I got a 50, another 50 here. Okay, I'm going to stop there. And I'm going to take a look at this average. Okay, let's see. Now, each one of these numbers represents a sample of size 9 from this population. Okay, I'm going to go back to my Excel sheet here. Okay, in my Excel sheet, let's see. Here we go. I'm going to say, one of the things I'm curious about, what's the minimum number and the maximum number here? Equals minimum. Okay, the minimum number, the smallest number here, is 27. And the largest number here is 69. Okay, so I'm going to start with that. Would you guys, yeah, I rounded those because I just want to be able to get this done quickly and not spend all night on it. Okay, I want to be able to get some other stuff here. So in the population itself, the range of values was 27 to 69. Now, you took samples of size 9, right? So would you expect the range of values here to be wider or narrower than in the population? What do you think? Is that minimum, the lowest value is going to be more extreme or less extreme than in the population? Okay, somebody give me an opinion. Give me narrower. It makes sense, right? Because the likelihood that you would get 9 people randomly that are all near this bottom number, this smallest number, is very unlikely, isn't it? So we'd expect the spread of these numbers to be less than in the actual population itself. In fact, the minimum comes out to be 42, and the maximum comes out to be 59. Quite different than 27 and 69. Okay, what do you think the average is going to be? Is the average going to be the same as the population? How do you think taking samples, the average of samples from the population, you think the average is going to be the same or different? Well, I think the more often that you sample from the same population, the more similar it's going to be to 50. And look, in fact, it isn't really 50. If I rounded this, it would round to something other than 50, right? But it's going to come close to 50. And the bigger the sample size, in other words, our sample size here is 1, 2. Our sample size is 9, but the bigger the sample size is, the more likely we're going to get close to that. Each individual one of these, the larger, if we had sampled 16 readings instead of 9, if we had sampled 25 readings instead of 9, we would have gotten even closer to the mean. Actually, we got pretty close anyway. Okay, we had a lot of these were pretty far. 42s. As we sampled 9 people, we got 42. We sampled 9 people, and got, so individually, each of these, wound up, could be a bit different than the mean, but certainly closer than, certainly not a terrible approximation of the mean. However, when we look at this distribution altogether, overall, if we just repeatedly took samples of size 9, and then we developed a new distribution, which was a distribution of the samples based on size 9, random selection of size 9 from that population, and we did many of them, you can see that we get very close to 50, very close to a good approximation of the population mean. Now, let's talk about the standard deviation. The standard deviation of the population was 9. What do you guys think is going to happen to the standard deviation of the samples from that population of size 9? Anyone who has a guess what's going to happen to standard deviation? Is it going to be similar to the one for the population, or is it going to be different? Oh, I got one smaller. You guys all agree it's going to be smaller? Well, the numbers are closer together, so the standard deviation is going to be smaller. And in fact, it comes out to be 4. Okay, the population standard deviation was 9. The standard deviation of the repeated samples of size 9 is 4 instead of 9. It is smaller. Well, in fact, mathematically, what it turns out, if you just continue to take any number of many samples of size 9 from the same population, what you're going to find is that the population standard deviation, I'm going to go back to my notepad. Okay, what you're going to find is, oops, it's not cooperating. Come on, drag up. What you're going to find, I'm going to get a fresh piece of paper here. What you're going to find that if the population standard deviation looks something like this, right? If you take repeated samples of, say, size 9, say 9, it might look, those repeated samples might look something like this. It'll look narrow, standard deviation is smaller, but the mean's about the same place. It's going to approximate the mean, but the standard deviation is going to be smaller. If you take a larger sample size, say size n equals 30, well, in that case, what's going to happen is you're averaging 30 numbers. So all of the numbers are going to be probably closer to the mean. So the distribution may look more like this. It gets narrower and narrower. The mean, X bar, approximates the mean in all of these cases. However, the standard deviation for each one of the sample distributions is smaller and smaller based on the sample size. In fact, mathematically, it's equal to the standard deviation of the population divided by the square root of the sample size. In the population that we were looking at, the standard deviation was equal to 9, and the sample size was equal to 9. So what would we expect the standard deviation of repeated samples from that population of size 9 to be equal to? What would we anticipate that standard deviation of repeated samples is going to be? It's going to be equal to the standard deviation of the population, 9, divided by the square root of 9, which is 3. 3 over 9 over 3 is going to be equal to 3. Standard deviation is 3. When we did it, we actually got 4, but we didn't take that. We only had a certain number of values. In fact, it might be 3.8 something. Remember, I rounded all those numbers anyway, right? So we just demonstrated what would happen if we had a sample of size 9. Why is this important to us? This is important to us because we're never going to deal with a population. We're always going to be dealing with samples, and we're going to have to make our judgments about what the population is like based on what we find in our sample. So we really need to understand how samples work. Okay, and this understanding, this central limit theorem, the idea that that as we take repeated samples from a population, random samples from a population, that we can predict what the mean, whether or not we're predict what the average, what we can predict, we can estimate or predict the mean of the population based on the sample, and we can also based on the sample, have an idea about what the standard deviation is. If we know what the population standard deviation is, we have an idea of how spread out the numbers in the sample should be as well. We can also work backwards if we really want to. So this is important to us. It's going to be very important to us moving forward. The other thing that's interesting about this thing called, I'm going to abbreviate it here, central limit theorem. The other thing about it is that let's say we have a population that is not quite not is skewed, right? Is like let's say it looks something like this. It's skewed to the right. That's what the population looks like. Well, when we take a sample from that population, we're going to blindly pick a person from somewhere in this population. Let's say right there. And we're going to go back and take another sample, blindly take a sample from there, blindly take a sample from there, blindly take a sample from there, and so on and so forth. Well, when we look at repeated samples, let's say we did that same way we did it now, sample size equals 9. When we take repeated samples from a population that's not perfectly normal, the distribution of the sample means that we would get by repeatedly taking a sample of whether it's size 9 or 25 or 50, the standard the distribution that we would get from that would be relatively normal compared to how skewed the population is. So we get a big advantage. There's another big advantage to this central limit theorem. Now, not only can we make predictions and understand distributions for normal distributions and how samples are related to those normal distributions, but we can actually apply this to populations that aren't perfectly normal. Now, I don't expect you to understand the math on why this occurs, but just trust me for a while and understand that, like, now it empowers us to be able to do this. So now let's apply this and see what this does for us. Okay, I'm going to go back to that Word document. Okay.